We've talked about blood pressure, blood flow. Let's talk about how stuff actually gets out and into the blood. So capillaries are where we have exchange with the tissues. So it occurs across capillary walls between the blood and the tissues, or the ISF. Things are usually actually coming out of the capillaries into the ISF, and then they're subsequently taken up by nearby cells. So particles escape across the endothelium of continuous fenestrated and sinusoidal capillaries. All capillaries allow things out. Mechanisms include diffusion, filtration, reabsorption, transcytosis, all those from Bio 156. Just has to do with kind of whether they're under pressure or not, whether they're going in and out. So lipid-soluble substances get out really easily, and you've known this since the first day of class, all right, because they can easily cross cell membranes. Steroid hormones, gases, fatty acids, small nonpolar molecules easily get out. Non-lipid soluble substances generally pass through using mechanisms like channels, transporters, fenestrations, intercellular clefts, and so on, all right? So they either need help or they need a really big space. So glucose, ions, polar molecules, large molecules, and so on, they have more difficulty getting in and out. Red blood cells and most proteins are too big to escape. So anytime you see blood in the urine, something's probably going wrong. Same with proteinuria. Proteinuria. If you've got proteins in your urine, something's probably going wrong. Normally proteins should not be able to get out of the blood. Now, capillary exchange is all about opposing forces. Remember, back early on we talked about hydrostatic pressure and osmotic pressure. Hydrostatic pressure is basically the weight of the water itself. That's water like coming through a garden hose. Osmotic pressure, remember, has to do with the number of solutes in the solution. So capillary exchange, opposing forces to move fluids and particles. Some forces drive or pull fluids and particles out of the capillary. They either force them out or pull them out, basically push them out or pull them out. So blood hydrostatic pressure pushes fluid out of the capillary. That's the weight and pressure of the blood itself. That's going to be forcing blood out. So when the heart pumps, the blood comes out of the heart, and then it's going to be under pressure, and that's going to force it out of the capillaries. That's high on the arterial end and low on the venous end. That's because arteries have the pressure, veins don't, and it's across the capillary where the pressure is going to go downhill as things leak out. Interstitial fluid osmotic pressure, IFOP, pulls fluid out. So think about it. There are solutes in the interstitial fluid. Remember, water follows solutes. So those solutes are going to be pulling water towards them. That will mean pulling water out of the blood. Now that's relatively constant. That doesn't really change very much at all, because from one side of the capillary bed to the other, there's roughly the same number of solutes. Then other forces drive or pull fluid and particles into the capillary, all right? So interstitial fluid hydrostatic pressure drives fluid in. So once again, there's actually fluid out there. The ISF is fluid, and simply the weight of that fluid is going to be pushing fluid into the capillaries. That's also going to be relatively constant. Then there's what's called blood colloid osmotic pressure, the BCOP. That's going to pull fluid into the capillary. So again, these are the solutes in the blood. Remember, water follows solutes. So the solutes in the blood are going to be pulling water in. That results in part from large plasma proteins like albumin and like the globulins and so on. They will be pulling water towards them. That's also relatively constant. So notice 3 of the pressures are relatively constant. The one that differs from one end to the other of the capillary bed is going to be that blood hydrostatic pressure, and so that's mostly what drives the movement of fluid and solutes. So here you see a diagram, NFP or NRP equals BHP plus IFOP minus BCOP minus IFHP. So net filtration pressure, that's going out, or net reabsorption pressure going in, is blood hydrostatic pressure plus interstitial fluid osmotic pressure minus blood colloid osmotic pressure minus interstitial fluid hydrostatic pressure. It looks confusing like that, but remember, all these things are just the force of water either being pulled or pushed either by hydrostatic pressure or by osmotic pressure. Under normal circumstances, capillary exchange depends mostly on the difference in blood hydrostatic pressure between the arterial and venous ends of the capillary. So what goes on here is on the arterial side, there's lots of hydrostatic pressure. That's coming from the beating of the heart itself and the force of blood being pumped through the arteries. So on that end, it's going to be pushing stuff out. Well, once lots of fluid and solutes especially leak out, then what's going to happen is once we get over to the venous side, there are going to be more solutes relatively inside of the blood, and there's going to be less hydrostatic pressure, and that's going to favor then water and solutes getting pulled back into the blood. So they get forced out on the arterial side, they get pulled in, for the most part, on the venous side. Now wait, won't the same things be going in and out? No, because on the arterial side you're getting the nutrients. Those are getting forced out. Those are going to be taken up by the cells. The cells then are excreting waste products, and those waste products are not going to get sucked in on the arterial side because most of the flow is going out of the blood. Instead, once the hydrostatic pressure decreases over on the venous side, now the osmotic pressure is sufficient to start pulling those waste products in. Things like we talked about, urea, lactic acid, creatinine, and so on. So the arterial end normally has a net outward pressure, and NFP equals net filtration pressure. The venous end has a net inward pressure, NRP is net reabsorption pressure. So it's actually easier than it first might sound like. It's basically just a matter of the fact that you've got a lot of pressure going out on the arterial side, whereas the pressure, got that Rona, coming in on the venous side. Therefore, the nutrients and the good stuff goes out, and the bad stuff gets pulled in, okay? Let's then talk about what happens if fluid accumulates out there. What if you got too much ISF? So normally ISF fluid will get taken back in on the venous side. You also have the lymphatic system, which is normally supposed to recover a lot of that fluid. So if capillary filtration, an increase in capillary filtration, will cause more water to flow out. Why would that happen? If there's, for some reason, an increase in blood pressure, so if you got high blood pressure, or an increase in permeability, so that can be some alteration of the blood vessels. Poor venous return will cause that. If blood is having trouble getting back to your heart, then it's going to pool out in your body. That's going to increase the pressure pushing it out. Heart failure can result in pulmonary or peripheral edema, remember? And that's often because, then, of the fact that there's insufficient cardiac output, therefore blood is pooling someplace, either in the lungs or out in the body. Insufficient muscular activity. So remember, the skeletal muscle pump is what gets most of the blood back to your heart. If you're sedentary, then you're not using muscles enough, and therefore the blood may not get sufficiently pumped back to your heart. Kidney failure. So the kidney normally is supposed to filter things out of your blood. If kidney failure, it's not working correctly, then you can end up with an impaired capacity to get fluid back in, and therefore you end up with edema. So histamine, kinins, allergic reactions, remember those are all vasodilators. Vasodilation means more blood to the area. That means more water leaks out, therefore edema. You can also have it happen not just because of increased capillary filtration, but because of decreased capillary reabsorption. So things like hypoproteinemia, not enough proteins in the blood. So like hypoalbuminemia, all right, if you don't have enough albumin, then you don't have enough osmotic pressure pulling water back in. So hypoproteinemia will lead to then edema because you don't have enough osmotic pressure to pull water back in. Cirrhosis, a disease of the liver in which it's not functioning correctly, therefore it's not making as many plasma proteins, therefore you have lowered osmotic pressure. Same with famine, burns, kidney disease. All those lead to too few proteins in the blood, therefore they're not pulling water back in as they should. And obstructed lymphatic drainage, remember the lymphatic system is normally supposed to recover fluid. If it's not working correctly, so cancer, radiation, removal of lymph nodes, and so on, if it's not working correctly, then it can't pick up all the fluid it's supposed to, and then fluid accumulates in your tissues. There you see somebody on the left. They've got an edema. There on the right, you see as well. The one on the right would look maybe more like obstructed lymphatic flow because it's only happening on one side. That probably wouldn't be heart failure. Yeah, Rona. And then you can see a typical way of testing edema. You poke, and then if it doesn't immediately come back, that's a sign that there's edema. So look on the right. We've got peripheral edema, so blood accumulating and therefore water accumulating in the lower extremities. So what do you think? Is that going to be right side heart failure or left side heart failure? We learned how to figure that out. Pause the video, figure it out. Yeah, right side heart failure. Remember, if the right side of the heart fails, or it can't pump enough blood, then blood is going to accumulate. Remember, the right side is trying to pump to the lungs, so if it's not strong enough to do it, if it can't get enough blood to your lungs, blood is going to back up in the body. And because of gravity, that's going to pull it down to your feet. So why is edema bad? I mean, so what if there's too much fluid out there? Well, let's take a look. Tissue necrosis. So if fluid accumulates, it may push tissues away from blood vessels. And then the blood vessels don't get enough oxygen and nutrients, and then you start getting necrosis, death of the tissue. You can see in the lower right illustration there, that happens a lot with diabetics. Diet for a little bit different reasons. Diabetics, because of all the glucose in their blood, the blood vessels kind of get roughed up. It's like sandpaper. And so you lose blood flow to tissues, and when you lose blood flow to tissues, then the tissues are going to die. So pulmonary edema can result in suffocation. Water fluid accumulates in your lungs. Cerebral edema, that's going to be like you see in the lower left, the swelling of the brain. That's a rat brain or something. But so what's going to happen there? Well, the brain is not going to function correctly. Headache, nausea, seizures, coma. Circulatory shock. So excess interstitial fluid results in lowered blood volume, therefore lowered blood pressure. And if you have lowered blood pressure, you don't get enough blood to the tissues, and then tissues end up going necrotic again. So circulatory shock, let's flesh this out here. That's a state in which cardiac output is insufficient to meet metabolic demand. So you're not putting out enough blood to the tissues of your body so that they get the stuff they need. So cardiogenic shock. That's, for example, inadequate pumping. So a myocardial infarction, a heart attack. Your heart's not pumping blood. Therefore, your tissues aren't getting enough blood. Low venous return, LVR shock. Hypovolemic shock, so trauma or burns, dehydration, where you don't have enough water or you're losing water, all right? You're not able to maintain sufficient blood pressure. Obscured venous return shock, tumors or aneurysms tumor may block blood flow, aneurysms, blood will leak. Venous pooling, vascular shock, so like sitting down extended periods of time. That's like on the airplanes, on the transcontinental flights. They'll normally suggest that you get up and walk around at some point. That's so your blood doesn't pool down there. Neurogenic shock, loss of vasomotor tone, vasodilation resulting from brainstem injury. All right, so remember the vasomotor control centers are in the medulla oblongata. And then anaphylactic shock. So this is where immune system overreaction to an antigen happens. As we'll see when we get to the immune system, oftentimes this is basophils and the IgE receptors. They kind of over-respond. You get massive histamine release, generalized dilation, therefore increased capillary permeability. You've got too much blood out to the tissues, therefore water is leaking out. Therefore the rest of your body is not getting enough blood, and that's anaphylactic shock. It can happen to hymenopterans, things like bee stings, nuts, antivenoms, strawberries, household cleaners. Lots of things can cause your immune system to overreact. When you get that massive vasodilation, remember the factors that affect blood pressure, peripheral vascular resistance. If blood vessels dilate, PVR goes down. If PVR goes down, then blood pressure goes down, and now you're not getting enough blood out to your tissues. And then septic shock can occur in infections. Various bacterial toxins, for example, can trigger vasodilation, just like histamine does, and also increase capillary permeability. So all these things on this slide are referring to circulatory shock. This is where you are not getting enough blood to your body, and that's very dangerous. That's potentially life-threatening. You can see in the upper illustration there's somebody jabbing an EpiPen into their thigh. Typical reaction if you've got like nut allergies or bee sting allergies, why would that help? You should think that through. Why is that going to help? Pause the video. Yeah, so epinephrine, remember, that's going to influence alpha receptors and beta receptors. It's going to cause peripheral vasoconstriction, going to increase heart rate, increase contractility. All of those things are going to make blood pressure go up, and that saves you. And then down at the bottom, you see, those, my friend, are lug nuts. You know I'm allergic to nuts. So how does your body respond to circulatory shock? Well, you can have what's called compensated shock. This is where your body initiates mechanisms to counteract the shock, all right? So various homeostatic mechanisms to restore blood flow. So baroreflexes engage the RAA system, the RAAS. So remember, a drop in blood pressure in the kidney causes a release of renin, which then converts angiotensinogen to angiotensin 1, goes to the lungs, ACE converts to angiotensin 2, and then the whole cascade of things, aldosterone and ADH and so on. Review that, you need to know all that. So that will raise your blood pressure. Syncope, which is fainting, restores blood flow to the brain. Think about it. If you have low blood pressure, you're not getting enough blood to your brain. If you continue to try to stand up or sit up, your brain's going to go, look, you dumbass, we're not getting enough blood here. So what does the brain do? It makes you go unconscious. What happens when you go unconscious? You fall flat on the floor, your body levels out horizontally, and then blood will be able to flow to your brain. So when that happens, your brain is basically trying to save you by making you pass out. Now, what happens, though, if the body doesn't respond appropriately? That's decompensated shock. Now we're talking big trouble. Life-threatening positive feedback loops. So the drop in cardiac output can result in myocardial ischemia. Your heart muscle itself is now not getting enough blood. Therefore, you get myocardial infarction. That lowers cardiac output even more. See, that's a positive feedback loop. The worse it gets, the worse it's going to get. Slow circulation leads to disseminated intravascular coagulation, DIC. That's where blood starts to pool in your extremities, for example, and you end up forming spurious blood clots. That slows circulation, so you're not getting enough blood to your tissues. And brainstem ischemia, so not enough blood to the brainstem, loss of vasomotor tone, and therefore cardiac output goes down even further, leads to further ischemia. These are positive feedback loops, and they're potentially fatal. So notice in the upper right, when we say shock, we don't mean like, oh, wow, I'm shocked. Or even like, when you touch something after you shuffle your feet on the rug and you get that little electrical shock. That's not what we mean here. Circulatory shock means not enough blood getting to the tissues of your body. So TIA and stroke, going along with these general concepts here, TIA means a transient ischemic attack. So this is where in the brain, perhaps due to atherosclerosis, all right, atherosclerosis would be one example you can see in the illustration there. So you get kind of a narrowing of a cerebral artery. That means not enough blood flows to part of the brain. So that part of the brain then starts not working correctly. Dizziness, loss of vision, weakness. You get the spots in front of your eyes, headache, aphasia, suddenly you can't talk. This is often an early warning sign of impending stroke because what it means is that you've got an artery that's partially clogged and you're having these TIAs. If things get worse, the artery may get completely clogged and then blood can't flow through, and then we get to the next thing, which is stroke. Stroke used to be called cerebrovascular accident or insult. They told us to not call it that anymore, I think because accident made it sound like it was somebody's fault or something. I don't remember. This is a brain infarction caused by ischemia. So remember, infarction means that basically the tissue is dying from not enough blood. And so now, what happens when brain tissue dies? Yeah, that's pretty bad. So again, atherosclerosis can cause this, a thrombosis, a traveling blood clot, aneurysm that bursts open. All of these things can lead to not enough blood getting to a certain part of the brain, and that's going to lead to stroke. The effects range from unnoticeable to fatal. There are people who have strokes and don't even really know they've had it until later they notice loss of function or whatever. And sometimes people just die right on the spot. My uncle woke up one morning and he just had a bad headache, went into the kitchen. My aunt said, "I'll get you an aspirin." She left the room, she came back, he was lying dead on the floor. That's how fast it can happen. He had an aneurysm in his head, just burst open, and within a matter of a minute, he was dead. So, effects can range from blindness, paralysis, aphasia, numbness, and so on. It just depends on which part of the brain. Occipital lobe, that would be blindness. Aphasia, the left side, remember, the temporal, the Broca's area, Wernicke's area. Recovery depends on surrounding neurons and collateral blood flow. So like the circle of Willis, the cerebral arterial circle, the idea there is that even if one thing gets blocked, maybe there's a way to get the blood there following another pathway. All right, so TIAs and strokes, very common. Okay, a decrease in which of the following would lead to edema? BCOP, IFOP, BHP, none of the above, or all of the above. Man, if this isn't the question from hell, I don't know what is. But a decrease in which would lead to edema. Look, stop the video, think it through. Okay. Blood colloid osmotic pressure is the force that pulls blood back in. So if there's not enough of that, then blood will not get pulled in. It'll stay out there, and then you have edema. Okay, that's it.